Our first presentation. The first presentation is from Dr. Shimizu. Dr. Shimizu is with Media Links. He is a manager in research and development in the research and development division. And he's going to present a paper about non-blocking multicast networks for transporting stream media. Dr. Shimizu, you have the floor. Please.
Okay. Okay. All right. Okay. Thank you, Hans, and good morning, everyone. Today, I talk about a new theory about non-blocking multicast networks. And recently, a large data center uses a so-called leaf-spine architecture. Leaf-spine architecture for a scalable network infrastructure. And this idea can be used for our application as well, media transport service. However, there is a difference. Data center traffic is mostly a unicast and best effort. However, our application requires assured multicast. So our design goal is to design scalable, cost-effective, non-blocking multicast networks. Okay. So this is the outline of my talk. First, I talk about the non-blocking multicast networks and focusing on two conditions. One is a so-called wide sense non-blocking condition. The other one is called rearrangeable non-blocking conditions. And I introduce a new theory to achieve these two conditions. Then I map these structures into the leaf spine networks with commodity switches. And then we have some evaluation, and I conclude my talk. So historically, non-blocking conditions have been discussed using this three-stage cross networks, which was formalized by Charles Cross almost 55 years ago. And the original network consists of these three stages and a crossbar unidirectional connections. And we have R1 input switches here, and M middle switches here, and R2 output switches here. Each input switch has N1 inputs, and each output switch has N2 outputs. So each switch is capable of a multicasting, and so the goal is to achieve the entire multicast through the entire network. In total, we have N1 times R1 inputs here, and N2 times R2 outputs here. Okay, so when people talk about non-blocking conditions, three categories have been addressed. One is a strictly non-blocking. The second one is wide sense non-blocking. The third one is rearrangeable non-blocking. The first one is it achieves a multicast without any constraints. The second one achieves multicast as long as we follow some algorithm. The third one is a multicast is enabled if existing multicast are rearranged. So in our application, WSNB is wide sense non-blocking is sufficient. And we can use a rearrangeable non-blocking class if we use, for example, 2022-7 HITRAS. Okay, so first we look into wide sense non-blocking conditions. Some conditions have been studied in a long history. And, but if you look at this, all of the conditions have a N1, this is the number of inputs per input switch, N2, number of outputs at output switch, and R2 is a number of output switches in the constraints. Here, I propose a new condition, which is independent to both number of input switches and the number of output switches. Simply, it say the number of middle switches is sufficient if you have at least N1, N2 switches. Okay, so here's the proof. Let's assume we have only one output per output switch. In this case, N1 middle switch is sufficient because you can pick up one middle switch here, and then you can pick up input switch here, and all the reachability is guaranteed. Now, that means that if you add another N1 switches to the network, then you can have one more output switches per output switches. So repeatedly, we apply these rules. So you can reach to N1, N2 is sufficient for the non-blocking, wide sense non-blocking condition. This is a proof by mathematical induction. Okay. So based on the new wide sense non-blocking condition, we define a distribution matrix here. The distribution matrix consists of in rows, we have middle switches. In the columns, we have input switches. And each cell represents that the input from particular input switch goes to a particular middle switch. Okay. And so as long as you have N2 fan out here, then it is guaranteed that N2 output of all the output switch is guaranteed. So this is the key of this idea. So N2 fan out for the inlet is sufficient to achieve non-blocking at the N2 outputs. Now, we go into the rearrangeable non-blocking conditions. Not so many studies have been done for these rearrangeable non-blocking classes. But again, if you look at these conditions, it has also the R2, or the number of output stages, switches, in the constraints. Now here, we use the proposed wide sense non-blocking condition and construct rearrangeable non-blocking class. Okay, if you look at this, this was a original wide sense non-blocking condition. We reduce some amount of middle switches here and still make it rearrangeable non-blocking. I'll explain this equation later, but it gives a upper bound of the input switches. So before I make some proof of rearrangeable non-blocking property, I show you how to design the RNB rearrangeable non-blocking network. So let's see, maybe I go this way. First, so we reduce the number of switches from a particular X inputs of all the input switches. That means we reduce X middle switches. So the lower bound is N1, N2 minus 1, if all the input has reduced fan out. Now then, I define D, it's a destination set. It's a set of the middle switches for the input. It goes to middle switches. Because we have a fan out N2 or N2 minus 1, the size of the set is N2 or N2 minus 1. Now, we can design the distribution matrix for rearrangeable non-blocking class. At this moment, we put some constraints for the design. For all the destination set D, where the size is N2 minus 1, identical sets are used at most n2 minus 1 times. And this is a key idea to make a rearrangeable a non-blocking class. And this gives a upper bound of the R1, the number of input switches, because in a distribution matrix, the number of rows is limited by this condition. Maybe it is difficult to imagine, so I'll show you some example. This is an example where we have 3 inputs per input switch and 3 outputs per output switch. The original wide sense non-blocking condition, we have 3 by 3 means 9 middle switches. Now we reduce 3, and then it becomes 6. In this case, the fan out of each input is reduced to 2 instead of 3. And then the number of a different destination set becomes 15 because you pick up arbitrarily 2 middle switches out of 6 middle switches. Each can be used twice. So the number of input switches limited to 10. If you look at this matrix, inlet 1 from input switch 1 uses middle switch 1 and middle switch 2. The same destination set is used only here from inlet 1 from input switch 6. The rule is kept through entire table. And now I just quickly explain why this is rearrangeable. Now, think about D0 is the destination set of the existing multicast. We focus on the one single output switch and think about how its subscribing source are distributed in the middle switches. So here we can see 3 cases. The case 1 is the distribution matrix size of the newly placed request is N2 at least. In this case, you have N2 fan out. So this is a non-blocking case, like a wide sense non-blocking condition. So this is fine. And the second case is all the inputs, all the source uses the same destination set, and its size is n-1. But in this case, the newly placed request has also size n2 minus 1. So this is sufficient. You can achieve a non-blocking condition. The last one is a newly subscribed and existing subscribed set has been distributed to N2 or more middle switches. So in this case, you can have enough alternative paths in the middle switch. So you can rearrange the existing path, and you can place for these newly placed requests. Now I show you some example. So in this condition, I use the same matrix, and inlet 1 from input switch 1 is subscribed to a particular output switch through middle switch 1. And you also subscribe inlet 1 from input switch 2 from middle switch 2. Now what happens if a new request coming in from inlet 1 from input switch 6? Both middle switch 1 and 2 are already used, but you can see the alternative path for inlet 1 of input switch 2 to a middle switch 3. So simply, we move it to middle switch 3, and then you can make a path for the newly placed request. So we made a new non-blocking multicast 3-stage cross network, both for wide sense non-blocking and rearrangeable non-blocking. Now, the next step is to map these cross networks to a leaf-spine architecture. Well, 3-stage cross network can be easily mapped into a leaf-spine networks. You can fold the network to like this. So in this case, the input switch and output switch becomes a leaf switch, and link becomes bidirectional. And if you have different numbers for the input switches and output switches in the original cross network, then simply some of the leaf switch works input only or output only. Okay. So, and now you can replace these links, single link in the cross network, to a bundle of Ethernet links, for example. Let's say K Ethernet link can be used here. And also, if the input and output, particular input and particular output, uses the same leaf switch, just you can bypass middle switches, and you don't have to go uplinks. Okay. Now, in our new condition, all the inputs are well distributed to the middle switches or spine switches. So every inputs are already distributed here, so you don't have to worry about the blocking condition in the middle stages. So this means you can apply this idea to even for the packetized network. Now next, let's calculate the size of mapped network. Assume that we have P1 ports for the building block switches for spine, and P2 building block switches for leaves. And let's say we have each cross network link is substituted with K Ethernet links. You may have some remainder, but still it works, it's okay. So now we consider the traffic from in and out for, for each spine and leaf switches, and make some conditions. From the conditions for the leaf switch, we can know how fat the bundle link is. And from the spine switch, we can see how many leaf switches can be connected to each spine switches. And consequently, we got a network size N1 P1 times N2 minus P1. So that is N1 times bigger input and N2 times bigger output compared to the original spine switch. Okay, so I introduced one technique that we can use after the mapping. When the number of output switch is greater than the number of input switch, the original cross network, then we may have output-only switches in a mapped network. In this case, in example, we have 4-port building block switches. And based on the rearrangeable non-blocking condition, we have only one input switch allowed, and we can have 4 output switches. That means only one switch can work as a bidirectional, and the other 3 is just output only. However, we have 2 middle switches here. And so if you have N2 fan-out means 2 fan-outs, you can use the input as a wide sense non-blocking condition. So we pick up each one input from these switches, make it 2 fan-outs, and then these inputs becomes wide sense non-blocking. So this is a good technique to increase the number of input port sizes. Okay, so in summary, the proposed method had 3 benefits. One is it is independent to the number of output switches. So we can use all the leaf switches for output purpose. The secondary, by the technique I introduced in the last page, we can utilize the dead inputs of the output-only switches. The second, we define the distribution matrix statically and predefined. So this routing information is installed in the input switches statically and before the operation. And we don't have to touch this. That makes it the multicast routing simple. The last one is for design, the distribution matrix. Based on the mathematical induction proof I did the first time, it is possible to make a bigger distribution matrix from smaller distribution matrices. So it allows easy design for the bigger matrix design. Okay, so let's look at how efficient the new method is. First, just for simplicity, we assume the spine and leaf switch has the same structure, same port count. If you look at the network, we have so many parameters, but this is just finite space. So we thoroughly search the combination of the parameters and get a best result for a given network size. The given network size is defined around 10 times bigger than the base switch. And I made a comparison for the known wide sense non-blocking conditions and rearrangeable non-blocking conditions. Okay, this is a result when we assume a commodity, commercially available 96-port building block switch. The left graph shows cases for symmetric network, n by n. And this part is just for the area for the single switch covers. And if you increase the number of the ports in the entire network, you need more switches. The proposed method is here, number 3 and number 7. And wide sense non-blocking condition, the new one, gives best performance up to 4 times or 5 times bigger than the single switch. And a rearrangeable non-blocking class, the new one, performs well until 600 ports means 6 times bigger than the original spine switch. And when I get a asymmetric case, it looks like something like this. So you have a different port count for input and output, and you can see how many switches are required to build these networks. Now we look into the detail of these asymmetric case. This small corner is for the single switch region. And the left side is a comparison between the known wide sense non-blocking condition and new wide sense non-blocking condition. The gray area is the new method gives a better performance. So if you look at this, maybe it gives a better result up to 400-500 ports count. But it covers many areas like this. It doesn't scale so much, but still it gives a better performance for small but relatively practical area. Okay. This is a rearrangeable network class, so I think this is much covers wide area. Okay, last my conclusion. A new approach for wide sense non-blocking and rearrangeable non-blocking condition was shown. Both conditions are independent to the number of output switches. The proposed approach is focusing on the distribution at the middle stage. That gives some good benefits. So routing at the input switch is predefined, statically installed, and we can utilize a dead input ports and output switches in some case. It provides the smallest number of switches at relatively small but practical size of the networks. Port count is maybe up to 6 times bigger than the building block switches. Okay, so that's the end of my talk. Thank you very much.
Thank you very much for the presentation. Thomas.
Thank you for sharing your insight on your models. Without having had time to read the paper before the conference, I can't go into the details of the math, so I'm going to skip that part. My question has to do more with where the industry is going in terms of infrastructure. The way you presented the research appears to focus on fixed ports that are used in fixed configurations, with a trend towards virtualization, dematerialization, and the fact that we're moving workloads around. Does this model actually scale, or is it implementable in a dynamic environment where we have sources that are permanently moving?
I think that is a good question. So basically, original model assumes a fixed configuration. But as I explained, it is possible to extend the number of middle switches by adding another matrix to the outside. So theoretically, it is possible to expand these network size after the installation.
But can I do that in a dynamic fashion where the resources that are on the endpoints can actually be remapped within seconds, minutes, hours without having to rewire the infrastructure? The feeling I had from the presentation was if you have a fixed set of sources which are known to being inputs and or outputs, this model may provide some benefit. But if you're in a model where you're using off-the-shelf infrastructure, which may be an input now and an output in an hour and an input and output in 2 hours, the scalability may be challenged.
Yeah, I understand. But this condition specifies how many middle switches are required. You cannot extend the number of inputs or number of outputs exceeds the capability, multicast capability of the middle switches. So, but as long as your port count is inside these conditions, then I think you can do that.
Okay. I did have a second question. You don't touch on if this is all designed as a layer 2 and or a layer 3 infrastructure. My understanding from the presentation, it's mostly a layer 2 with a one-to-one port mapping, either bundled, as you mentioned, multiple, say, 10 gig ports into 100 gig port for the uplinks, but you don't touch on any routing. So would this be a layer 2 with a flat network?
Well, of course, that's a good question. So of course, you need to utilize the multiple links, multiple uplinks, for example, and you need to avoid a layer 2 loop, for example. So one good thing is to use, for example, OpenFlow to specify each flow's destination source to a particular port. Then you don't have to worry about these issues.
Okay, because if we were running 700 ports as a layer 2 domain, we might be seriously challenged. Okay, thank you.
Last question, Thomas?
Yeah, Thomas Edwards from Fox. Excellent improvement in the theory, and thank you so much for presenting this. Have you actually built any spine leaf networks based on your new theory?
We tried several experiments, but not a big one, just small ones.
Okay, good. Thank you, Dr. Shimizu. We move on to our next paper.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.